In life, we often take calculated risks. The purpose of statistics is to try to measure risks or to tame uncertainties by quantifying them. This is done by making educated guesses and deciding beforehand how large a risk we are willing to take if we are wrong. Think about this. We often make educated guesses or try to figure out the odds in coin flip, gambling, dice roll, and so on. We often make these educated guesses by setting a probability or confidence level. The probability or confidence level are at the levels we are comfortable with to estimate the percentages of time we are wrong. These probabilities are called p-values. They are closer to reality than random guesses because they are based on some kind of mathematical logic. A probability is essentially numerical measures of the likelihood that a particular event will occur. We often set a threshold for the calculated risk we are willing to undertake. This threshold is called the level of significance of the statistical test. The level of significance is signified by the alpha. The most common values for the alphas are 0.10, 0.05, and 0.01. These are the most common threshold for the alpha or for the level of significance. In most instances, we settle for a 10%, a 5%, or a 1% risk. Hence, 0.10, 0.05, or 0.01 are the most commonly used cutoff for statistical significance. Let's think back to our M&M example. It is entirely possible that we get several odd samples where the number of NMMs in these bags differ somewhat from what we normally get in a typical M&M bag. Thus, the means and standard deviation from these samples will vary somewhat from the more typical samples of NMMs. In this instance, the probability is essentially numerical measures of the likelihood that a particular M&M sample will look odd, meaning that there are either too few or too many chocolates in a bag. This probability is still measured by the p-value. Many people make the mistake by thinking that small p-values imply large differences between groups. They only imply that we are pretty confident that there is a difference between the two groups, or there is an association between the two variables. Bear in mind that statistical significance does not always translate into predictive accuracy because the p-value is affected by the sample size and variability. P-values do not tell us the magnitude of the differences. It only tells us the likelihood that the group differences may exist due to sampling errors instead of being the reflection of the groups coming from different parent populations. The p-value is often incorrectly interpreted as the probability that the null hypothesis is true. For example, suppose that a study on gender differences in mathematics achievement produced a p-value of 0.0232. This does not mean that there is a 2.32% chance that the null hypothesis is true, or there is a 2.32 chance of committing a type 1 error. The correct interpretation of p-value would be that there is a probability of 0.0232 that you will incorrectly reject the null hypothesis and claim that there are no gender differences in mathematics achievement. In other words, p-values tells you how likely are your conclusions under the conditions of the null hypothesis. It does not tell you anything about the research hypothesis. It does not indicate whether the research hypothesis is true. Here, you can see that the probabilities are also the rules that link the sample to the population. Most of the time, the accepted risk or probability varies according to our research question at hand. What if the research question is about the effectiveness of a new drug? In this case, you might want to be more certain before accepting the risk of being wrong. In other instances, there is little risk from being wrong and a 5% risk may be too strict.